And they further on define what characteristic is biometric characteristic, as you can see here. My original talk would talk about how the challenges of cross-modal for each of them, but I kind of summarized them to fit them in 30 minutes. But basically what it says is that, these days we hear a lot about new modalities like shoe print or tattoo, but they are not really biometrics, but they are a useful attribute to do pattern matching. As for fingerprints, the history of fingerprints goes back a long time ago. This is pasted from NIJ fingerprint sourcebook, and they talk about the first evidence of using fingerprint for identification back in 1600. Many of us know fingerprint as, or the beginning of the fingerprint for identification with the work that Sir Francis Galton did. What he basically did, he was one of the first people that formalized the comparison of the fingerprint by formalizing the characteristics and the discriminatory informations of the fingerprint that we are still using it today, that basically being the by minutiae, regending, bifurcations, and the singularity points. Then this will become used mostly, police and law enforcement and victim identifications, disaster victim identifications, start using applications of fingerprint for identifications, and methods for capture of the fingerprint developed. The earliest one was using ink and cards to capture fingerprint. Back then, the cross-modal was the type of the ink, the paper, anything that they use. And the result was, fingerprint card that the first two rows would be the rolled fingerprint, as you saw in the previous image, that somebody will go and roll the fingerprint. And the bottom row would be the simultaneous slab, the 4 fingers that was used for sequencing of fingerprint. Then the examiners would look at these fingerprints under, magnifier and try to distinguish those minutiae points and discriminatory points that was formalized by Galton to do the comparisons. What happened is that back in sometimes in 60s, the computer is the new thing, and they do things that human can do, sometimes better and definitely faster. And FBI got interested to use computers for fingerprint recognition and try to automate much of its fingerprint work. Back then, we were National Bureau of Standard, and we had some of the cool IBM machine, and even better, we had some scientists that could work on those machines, mostly for image and pattern recognition. So the FBI interest to use computers and automate their fingerprint matcher spurred a lot of debates in the media on the questions such as, can computers be a reasonable replacement for the eyes and brains of the human? Because you know that because of skin elasticity and all that, every time we leave our fingerprint, there is a little bit of distortions. And the question was, can computers handle these intra-variability of the fingerprints? Some of these questions, as you know, if you're in the fingerprint domain, is now applicable and being asked for lights out latent. That computer can do the lights out latent as it should be. Nevertheless, FBI went along and with a plan, it came to NIST, asked for NBS at that time for help, and that started a long collaborations in fingerprint research with FBI that still goes strong. NBS replied back by developing technical notes and documents and that which got adopted by FBI. And at that time, Jim Loudermilk told me that the first time that FBI automated their fingerprint, the markup of the prints were used to be done by the human, and algorithm and the computer were only used for the comparisons, which is again sometimes somehow similar to what latent is being done today. In the years that followed, now FBI's automated processing is getting advanced, it's getting better, but they were running into the problem of they were getting files in different formats and with different type of metadata, and they wanted standard way of storing and exchanging of fingerprint data. They came back again to NIST, and NIST convened this Canvas group to develop the first standard or specification for storage and exchange of the biometric, at that time, fingerprint. So in 1986, NIST developed and published the ANSI-NIST standard. The first version was only fingerprint, and again, it goes back to what Galton started by minutiae and singularity point and all that. Over the years, it has been developed, expanded. Now it contains many different modalities from DNA, voice, dental record, all that, and it has been used all over the world, as shown by this map. It's basically the standard way of exchanging biometric data for law enforcement. On the years that, another thing that happened with the ANSI over the years is they also came up with specifications for the sensors that capture fingerprint, as many of you know them as Appendix F. And go back to Appendix F a little bit later. In the years that followed the development of ANSI-NIST, our group were busy working on character recognition. Some of the deep learning book that I look at are using the MNIST data. So some of you guys working on deep learning probably are using MNIST data, and it's kind of interesting for me to go and see that they are still there. And also development of algorithms and codes for conformance, implementations of the specification in ANSI-NIST, and also release of public data. So along the way, we know that the importance of the public data for repeatable and reproducible research. And we are very grateful to IARPA and everything that we hear for development of more public data sets. Beginning of 2000, face recognition is the holy grail of computer vision. He started this evaluations of face recognition, and we were in the middle of that 9/11 happened. That becomes a kind of a turning point in all biometric research. The start of US visit, and NIST was tasked by certifying biometric technologies for government use. That started another test for fingerprint, and then many other tests on finger and face followed with a lot of more data and mandate to do more testing. In early 2000, the IRIS is being introduced as a viable biometric, so we stood up the IRIS program, which George is going to talk about them a little bit on. Later on, it has, over the years, it has done, I think, 10 evaluations. We're on IRIS 10 probably now. Infamous misidentification, the Madrid bombing got us into the world of the latent recognition and latent evaluations. Boston Marathon bombing got us into identification of person from the video, and this list continues. And over the years, what we have learned with our test is more data, better testing, better standardized way of reporting and metrics. One of the things that we learned along all of this is the garbage in, garbage out. If you have a biometric sample that doesn't have enough discriminatory information in it, the matcher can't do magic on it. So the upper limit for accuracy of the matchers is the information content of the input image. So if I give this to any fingerprint matcher, because it doesn't have that much of fingerprint information there, the matcher cannot do a reasonable job of identification or verification on that, regardless of the quality of the other sample that's being compared to. Some other time, the problem is that you don't have enough overlap. So this is a nice looking fingerprint, but it doesn't, it's from the side. And in another research that I don't cite it here, we show that the spatial location of the fingerprint has influenced the amount of information there, and therefore matchability of the fingerprint. So again, this is an example of the fingerprint that, despite the nice clarity, is not going to be matched because you don't get the enough overlap. Sometimes you don't have enough information because of the occupation, the condition of the skin due to occupation or age, or sometimes intentional manipulation of the skin. We addressed this problem back in 2004 by release of NIST fingerprint image quality, NFIQ. What it is really, it's a neural net that gets each fingerprint and classify it in one of the 5 classes of 1 to 5, 1 being good quality, there's enough information, the expected error rate is low, 5 being that it is poor quality, not much information, expected quality is low. That was basically the innovation of NFIQ, that the way it defined biometric sample quality. And that definition got adopted by standard community. It's applicable to other modality. And then in 2014, we were asked to do, because it's machine learning, it learns the type of the images that it was available and the technology that was available in 2014. In 2012, I believe, we were asked to work on a revision on NFIQ2 for something better, faster, with more resolution. That results in NFIQ2. This has been formally standardized as part of ISO IEC 29794. The implementation that we have at the GitHub is the reference implementation for the standard, but it also allows for other people to develop their own algorithm and do the plug and play. Again, this is a machine learning. This time, instead of the neural net, we use a random forest, and instead of 5 classes, it's on a scale of 0 to 100. The other thing that happened after the 9/11, remember that most of the fingerprint captures was through the ink card, and now with the algorithm being used, and then get the card, you have to scan it, put it in the computer. So they decided, the industry start working on capture of fingerprint. There are many different technologies for the capture of the one finger. This is the one in the middle, if I can get it to work. So this one, this is capacitive. Then I don't remember, I think it was in 2005 or 6 that DHS challenged the sensor community to come with a fast capture of all 4 fingers at the same time. As Nathan mentioned, there is interest on having a contactless, so people don't have to touch stuff. It has a lot of benefits, mostly on user experience. This poses some challenges and some advantages for fingerprint recognition, and as you know, many of the smartphones are now using fingerprint or other biometrics for authentications. The images that comes out of these sensors may look a little bit different. So this is a live scan optical, the one with the 4 finger on it, the capacitive, the ultrasound, and all the other one. They do look a little bit different. The distortion model along them are completely different. But because of Appendix F, and because for any of these sensors to get into the market, they had to pass Appendix F, that sort of regulates all the images that comes out of the sensors have similar look and feel. Still, the distortions are different, so the minutia-based matcher can match them just fine, and we are looking at evaluations of other technologies on them, which we probably present at BTAS. So this is the type of the images that you get out of them, and this is the type of images that you get out of the latent. The latent is now, it's manually lifted from the surfaces. Most common capture mode today is live scan for, they call it SLAP. Images comes like this. The challenge there is to go and segment the fingerprint, which is not a difficult thing. An algorithm does a fine job, and then you get the images like this. As Chris mentioned this morning, so that with the SLAP, they solved the problem of simultaneous capture of the 4 finger in a timely manner, but still for many of the rolled application, there's going to be an operator that grab the finger and roll it on a scanner, and this is kind of timely, expensive, you need an operator be there. So IARPA started the end-to-end challenge, which was a challenge to this industry to come up with a efficient, fully automated way of capturing nail to nail. The result is going to be, as Chris mentioned, next week, March 21st, right? March 21st, it's a Wednesday, but I keep mixing it, is it 21st or 20th? And there will be some other result, which I thought of, you can learn about it later on. How do we do on the accuracy? We ran a test. The last test on the fingerprint accuracy that we ran was back in 2012. We started in 2012 and we ended in end of 2013. So this is really 2013 technology. How the accuracy works, no surprise, as we go from 1 finger to more fingers, it gets better. So the 10 fingers give us the best performance down here. One surprise thing is that 2 finger, left and right fingers, if I get my right index and left index, perform almost the same as 8 finger and better than 4 fingers. So that was kind of interesting. But you can see that the state of the art is about is about here, 1 in 1,000 for a kind of a flat FPIR. How did it compare across the year? This is the previous evaluation that we did back in 2003, and it's just fair to say that in a decade they improved for like a order of magnitude. The other thing that our tests look at is the trade-off between accuracy and computational efficiency defined as the size of the templates, because you have to go and store them, and the time it needs to be matched. So what we have here on the x-axis, we have the median search template size. On the y-axis, we have 1 point on RRC, as Chris mentioned this morning. It makes it easier to compare. So our figure of merit is FNIR at FPIR of 1 in 10,000, and then we color-coded each of the points. Each of the points correspond to the one algorithm under the test with the search time. So really what we want things down here that's low performance, smaller template size, and we want them to be dark to show that the search time is also fast. But you see that you kind of see some sort of the clusteration. The more accurate algorithm use larger template size. Sometimes they use a lot larger template size for not much gain on the accuracy. And sometimes you have a better option that, with a little bit of sacrifice on accuracy, you get a really efficient template. These are all, you can read more with a lot of more results at this link. How do they compare with latent? So what I did here, I put the front finger accuracy out of the FPVTE, the test that I show you the result, with the latent accuracy. For one finger accuracy, we get something about 2% FNIR. For 1 in 1,000 FPIR, that number for latent is, the error rate is much, much higher. So a lot of challenge to be done for the latent matching, if the latent matching to exemplar can be classified as a cross-modal. What we had done on the latent fingerprint, so the first thing, again, going back to garbage in, garbage out, now with the latent, majority of the qualities are low. So the first thought that come to us is that if we can go and measure the information content of the latent the way we do it for fingerprint, then we can do some triage and then use the algorithm more efficiently or deploy better enhancement techniques. So what I show you here, is a method and algorithm that we developed with MSU, Dr. Jane's lab, that gets a latent and measure its information content or quality. And I put some examples here. There is a TIFF's paper that you can read the result. It does correlate with both automated matching algorithm accuracy and human examiner's accuracy. What are the challenges? Vulnerability. So when I showed you the poor quality fingerprint, I showed you the fingerprint that and said that the cause can be age or occupation or intentional manipulation of the fingerprints. So one of the things that's happening is that people go and do some customized surgery or whatever you want to call it to go and change their fingerprint to evade detection. And the other thing, as we heard about this morning, Odin is doing, is development of the fake fingerprints. This is some examples of real-world altered fingerprints. These are not fake fingerprints. So the people that go and do some surgery on getting their fingerprints altered. What we have done is we have used GAN to develop an automated way of detecting altered fingerprint. So our data set is something about 3,000 altered fingerprint, and this is the two implementation that we use, MobileNet and Inception, and we just use it as it comes out of the box. There's a GitHub that you can go get it. And then we use GAN to generate more altered fingerprint that I'm not showing here, but we're hoping to be able to get more altered fingerprint and work on it. This is, so we get about 92% accuracy at this false positive. The best result reported in the literature was 75% at 2% false positive. So the challenges and what needs to be done really is Yeah, I could have update this, but really what we need to do for all this cross-modal and for all of this, latent problems is try to find methods to measure the discriminatory informations of the features and then summarize them into the whole image. Cross-modal plays a role because you see different features, different informations at different levels. So for example, for NFIQ, we trained it, especially if you use all of this training algorithm, we trained them on live scan images. And I get, when we released them back in, I think, 2 years ago, I was replying like 10 emails a day. Can I use it on capacitive? Can I use it on ultrasound? The answer is not really. I don't know. I didn't have the images to work on it. So if we can find a way to measure these things and figure out the features that it's show itself across the domain and then measure the variance across them, it's going to be helpful. So with all this, we see ourselves back, and with all the questions, with the advent of the deep learning and all the data, I feel like it's the same questions that were asked back in 60s about use of the computers for fingerprint recognition is being asked here. Are they good enough? Can they do this? And if we can learn anything from history, I think probably. And with all of these things going, they're all going through objective methods. So the more we can get algorithms to do this, the better we can study the error rates and figure out what to do. That was my talk. Thank you.
Thank you so much. So do we have any questions? Yes.
Are there any demographic biases in recognition accuracy? Because that's a big thing with
Fingerprint.
face.
Yep. We have. For the little study that we did, we don't have a very large data set to do. We didn't see any specific. The thing is that while the reach thickness changes for different demographics and for different ethnicity, the distribution of the minutiae doesn't change. So that goes back to the population studies. The first thing that we did, we look at that one. Age. And I took those slides out. For the age, So-Won Yoon did some study and showed that the fingerprints permanence, the FNIR doesn't change. Then the question is, does the FBIR change as they get worse? FBI had done a study that is not yet published, but they look at the physiology and the biology of the finger and the layers of the skins, and they showed that as far as the recognition algorithm cares, the changes are negligible and cannot change them. The FBI paper should go out any day. It has been going out the past 1 year, right? But right, so that's as much as I know for now. But again, population study is something important.
Okay, thank you.
So I have a very quick question. So I think back a long time ago when they started looking into fingerprint recognition, there were essentially two basic approaches. There were the minutia-based, and then there was essentially this alignment and then image level correlation, which kind of dropped out because of all of the nonlinear deformations from collecting prints on a touch-based system. I'm curious if you have any thoughts or comments as we're moving towards more touchless-based systems where you don't have those deformations. Do you think we'll move back into looking at some of those image level correlation approaches?
Well, image level, maybe not image level correlation, but the texture matching, whatever texture matching means, yes. So, right, so one of the other tests that we did is MinEx, I think starting HSPD 12, that requires all the federal government employee and contractors to have a biometric enabled identification card. Then they wanted to put biometrics image there. And the card couldn't handle the full fingerprint image, so they put minutia. So we started this test to see if minutia-based matcher, if it just summarized all the informations in the fingerprint into the locations of the minutia and the angle of the minutia, is it sufficient information to do the matching? And what we learned is, yeah, you can do the matching, but you're going to get a hit compared to image-based matching. And then we look at the interoperability and all that. So yes, the minutia-based matcher had the advantage of you go and summarize the whole image into something smaller, maybe even fixed length if you limit your number of the minutia, but you get a hit on accuracy. Majority of the new papers, you were at the IJCB, everybody were talking about CNN-based fingerprint matcher, and what they're doing is they call it texture, and if you talk with them what texture is, but it's really image-based stuff. So everybody is now combining the two. So yeah, we are seeing ourselves back seeing them.
Exactly, full circle.
Yeah, full circle.
So when we're looking at cross-domain stuff, which this workshop is, right? So if I look at multispectral or other elements, right? One of the things you can do is one can do a bunch of image pre-processing to make things seem more relevant. And I can actually do image processing to make the image look like it has better NFIQ as well, right? So how does that fit within the standards and looking at, as people try and make their sensors look good with respect to those things, right? What are the rules or what are the processes by which you decide that that's appropriate image processing to make it so that the things line up and that's not?
That's a very good question. And when I know on the exhibit floor, people tell me that, oh, we have NFIQ there, and right, and I think NFIQ helped, but the other problem is that, as you just mentioned, everybody tried to make their fingerprint, manipulate their fingerprint with, I don't say enhancement, but processing techniques, so they cheat NFIQ and get good scores, which is a bad thing, right? At some point, I think the wish list. So for the latent stuff that we want to do, so the wish list of the challenges that we want to run is enhancement techniques and figure out different enhancement technique and processing technique, what they do and how they can be used. But talking about regulations or what needs to be done, I don't know. I understand the problem, and I know that it's a problem. But is it any type, can we solve it with any sort of regulation? Probably not. Can we go on and solve this problem that NFIQ? I don't know how to solve that problem. I don't know. But that's also true for the MINEX text. That I don't know if you look at the MINEX 3 test. So one of the things that we saw in the MINEX test is that people were marking up or extracting minutia at a lower resolutions at 300 ppi, and then they would extrapolate it to 500 ppi. Therefore, when you plot the PDF of the minutia points across many images, you see this grid phenomena. And then we came and said that, no, that's bad. In a normal fingerprint, you are not going to see this grid. So we tightened the rules and say, you cannot have this grid base. So what do the participants do now? They just add a little bit noise on the locations. It doesn't solve the problem of the grid, but it, in a way, hide it. So we run into this problem, and I think every time we try to come up with another way. If you have any ideas, I'm happy to listen, but I don't know. It wasn't the purpose of NFIQ when we did it, but it started using it that way.
All right, so let's thank Elham again.
All right, we have another keynote coming up. So Mr. George Quinn is a researcher at the National Institute of Standards and Technology. He has been involved in various biometric technology evaluations, including the face recognition vendor test, the evaluation of latent fingerprint technology, and the multiple biometrics evaluation, still face test. He currently leads the latest iteration of the Iris Interoperability Exchange Program, IREX. His research interests include biometric sample quality, biometric fusion, and statistical computing. So, we're very pleased that somebody with so much experience can